All right. So, hi, grade 12s. I hope that you're all doing well. This is Mr. Musklo. And as explained in Google Classroom, your work today consists of 3 tasks. So, you have 3 tasks to do for your asynchronous work today. Your first task is to read this excerpt about carbon. Your second task is to watch this video. In this video, I'm going to explain today's material. In this lesson, we're learning about the structure and properties of solids, which is a topic that I quite like. I know it might seem like I say this about every topic, but I do think that this stuff is kind of cool. And then your third task is to read another excerpt about glass. So you might not have realized this, but this attachment has 2 excerpts. So the first half of the document is the excerpt about carbon. And then the second half is about glass. Now, both of these excerpts are taken from the same book. The book is called Stuff Matters: Exploring the Marvelous Materials That Shape Our Man-Made World by Mark Majadownik. And as the title of the book suggests, the book basically gets into the chemistry of a variety of materials that we come across and use in our day-to-day lives. Things like glass and graphite. You might not have ever wondered before what glass is made of chemically, but this book explains what these materials are chemically. So hopefully you enjoy these readings. Kind of gives you an opportunity to see glass and graphite, the material that makes up the tip of your pencil, a little differently. And so, yes, do make sure and read this excerpt about carbon before watching this video. So, excerpt about carbon first, then video, then the excerpt about glass. All right. So, yes, our lesson today is about the structure and properties of solids. And the opening slide in this PowerPoint shows some different examples of crystals. So in chemistry, a crystal is simply a solid that has atoms arranged in an orderly arrangement. So the first crystal shown is an ionic crystal, which we're going to talk about in this lesson. The second image shows what diamond is made of chemically. So diamond, we're going to see, is made of pure carbon. When the carbon atoms bond together in a tetrahedral arrangement, you have diamond. That is what diamond is chemically. It's made up of these tetrahedral crystals. And we're going to see that these types of crystals are called covalent network solids. So we're going to learn about covalent network solids in this lesson. And then we also have an example of a molecular crystal on the right. So a molecular crystal is just a crystal that's made up of molecules instead of ions. And this molecular crystal in particular is an ice crystal. Again, we've talked before about how the shape of a water molecule makes it so that in an ice crystal, the water molecules arrange themselves into hexagon shapes. And so this is actually why a snowflake is 6-sided. It's because the water molecules are forming these hexagon-shaped crystals. But we're going to talk about that in this lesson. Okay, so let's start out by talking about ionic crystals. So ionic crystals, as the name suggests, are just crystals that are made of ions. And this slide shows a sodium chloride crystal. So in a sodium chloride crystal, you have sodium ions and chloride ions, right? This is what sodium chloride is. It consists of sodium ions and chloride ions. And you'll notice that the sodium and chloride ions are arranging themselves in a very orderly arrangement. They're actually arranging into kind of a cube shape. The reason why the ions do this is simply because opposite charges attract. And so every ion is going to surround itself with ions of the opposite charge. And so this image makes that point. We have a sodium ion in the center of this cube. And you can see that this sodium ion is surrounded by chloride ions on all sides of it. So it has a chloride ion above it, and below it, and in front, and behind, and then off to the right, and off to the left. So this sodium ion is completely surrounded by chloride ions, and the ions arrange themselves in this way, again, simply because opposite charges attract. So this sodium ion is positively charged. It's going to surround itself by negatively charged ions. Okay, and likewise, every negatively charged ion is surrounded by positively charged ions as well. So this chloride ion has a sodium ion behind it, and to the right of it, to the left, in front of it. So every ion is surrounded by ions of the opposite charge. And so if the ions are arranging themselves in this way, this means that they will actually arrange themselves into a cubic shape. And so there is an image on this PowerPoint slide of what sodium chloride looks like under a very powerful microscope. So this image was taken with an electron microscope, and it's showing sodium chloride crystals. Now, sodium chloride, of course, is just table salt. So really what we have a picture of here are just grains of table salt. If you look at table salt just with the naked eye, you'll notice that they are cube-shaped. But this image just makes very clear that, yes, they really are cubes. And they are cubes because of how the ions arrange themselves in the crystal. So that's ionic crystals. Now, we'll talk about metallic crystals as well. So whenever a metal is in its solid state, the metal atoms will actually form metallic crystals. So metals are made up of crystals. We don't often think of metals as being made of crystals, but they are actually made of these crystals that are also sometimes called grains. So you'll hear them referred to as grains as well. Now, the reason why we perhaps don't usually think of metals as being made up of crystals is because we often can't see them. In some cases, we can see them, but in a lot of cases, the crystals are just too small to see with the naked eye. And so when we look at a piece of metal, it just isn't clear that it's made up of crystals. But this image shows some steel under a microscope, and you can see that it's made up of these grains. And in each of these grains, the metal atoms are arranging themselves in an orderly arrangement. Okay, so often these crystals cannot be seen with the naked eye. In some cases they can be, though. In some pieces of metal you can see that it's made up of these grains if they are large enough. Now, we'll just talk a little bit about what's actually happening to the atoms in a metal, because we haven't really gotten into that topic in this course yet. We've said already that metal atoms tend to lose their electrons very easily. This is what it means for an atom to be a metal atom. It just means that it has a weak hold on its electrons. So in a solid piece of metal, you have a bunch of these metal atoms, all of which have a weak hold on their electrons. And so what takes place here basically is that none of the electrons are really bound to any particular metal atom. Since the metal atoms have such a weak hold on their electrons, the electrons are just kind of free to move about amongst the metal atoms. And so the picture kind of looks like this. We just have positively charged metal ions in a sea of electrons. And this is sometimes called the electron sea model because it kind of visualizes a metal just as an array of positively charged ions with a sea of electrons that move freely amongst those ions. And this can actually help us explain some properties of metals. The reason why metals conduct electricity is because these electrons are free to move. So if you applied a voltage to this piece of metal, the electrons would move in response to that voltage. So metals conduct electricity because the electrons are free to move around. This can also help us explain why metals have such high melting and boiling points. Each of these positively charged ions are attracted to the electrons that are in this electron sea. And so it's going to require a lot of energy to separate these ions. And so that is why metals tend to have high melting and boiling points generally. It's because these ions are quite strongly attracted to the electron sea. Okay, so that's a bit about metals at the atomic level. Now, this is nothing new, really. I've explained this a few times because I think it's kind of interesting. This PowerPoint slide shows some water crystals. So, as explained before, whenever water freezes and becomes a solid, the water molecules arrange themselves into a hexagonal crystal. And this is why snowflakes have 6 sides. So this is an example of a molecular crystal. A molecular crystal is simply a crystal that's made up of molecules instead of ions. So ionic crystals are made of ions, molecular crystals are made of molecules. Okay, and of course, water molecules can form these molecular crystals because of the hydrogen bonds between the water molecules. So in order for these crystals to form, there has to be intermolecular forces between the molecules. All right, so we're going to talk about covalent network crystals as well. So a covalent network crystal is basically a solid where the atoms form an interwoven network. And it's perhaps easiest to understand this idea if we just compare it to the other types of crystals that we saw. So in a molecular crystal, you can see that the crystal is made up of these water molecule units. And each of these water molecules are separate from each other. So this water molecule has an oxygen atom bonded to 2 hydrogen atoms, and it is its own unit. And then this water molecule also consists of an oxygen bonded to 2 hydrogens, and it is its own unit. So these two water molecules are separate from each other. Of course, there are intermolecular forces between them, but they are not covalently bonded to each other. So they're separate molecules. But things are different in our covalent network crystal. In our covalent network crystal, you can see that all of the atoms are bonded to each other. And so they're all interwoven into this network crystal. And the covalent network crystal shown on this slide is diamond. So in a diamond crystal, you can see that we have carbon atoms bonding together to form a tetrahedral shaped crystal. And so that is why natural diamond crystals have a tetrahedral shape. This image shows just some natural diamonds. And they take on this shape because of the way that the carbon atoms are bonded together. Now, the reason why diamond is such a strong material is because all of the carbon atoms are bonded together in the crystal. And so that makes it very strong. It also has a very strong shape. The tetrahedral shape gives it strength. And so diamond is the hardest naturally occurring substance on Earth. And it really comes down to the fact that it is a covalent network crystal whose atoms are bonded together in this way. Now, if we just cast our minds back to what we had learned about earlier in this unit, let's just ask ourselves what the hybridization is on this carbon atom. So this carbon atom has 4 groups around it. It's formed 4 single bonds. And so that means that it's sp3 hybridized. Okay, so all of the carbon atoms in this crystal are sp3 hybridized. And so that means that they make a tetrahedral shape. Now, in graphite, things are a bit more complicated than we saw in diamond. Both graphite and diamond are made entirely of carbon atoms. So they're both pure carbon. The difference between graphite and diamond comes down to how the carbon atoms bond to each other. So the carbon atoms bond to each other differently in graphite than in diamond. And as explained in the reading that you did, it turns out actually that carbon atoms are more stable in graphite than they are in diamond. So graphite is a more stable form of carbon than diamond. The carbon atoms in a diamond crystal actually want to look more like the carbon atoms in graphite. And so that does mean actually that a diamond left on its own for billions of years will actually slowly turn into graphite, just because graphite is the more stable form of carbon. And so we're going to learn here how this works, what is happening to the carbon atoms in graphite. For now, I'll just mention that graphite basically consists of these layers or sheets. And these layers or sheets are weakly attracted to each other. So they aren't strongly bound to each other at all. They separate relatively easily. And so this is why graphite is a much softer and more brittle material than diamond. It's because these layers can separate easily. You don't need to look far to find graphite. Graphite is actually the material that makes up the tip of your pencil. Now this part of the pencil we often call lead. We call this the pencil lead often. That's a bit misleading because it isn't actually made of lead, although it does kind of look like lead. The ends of your pencil are made of graphite. Now, if you just look closely at our image of graphite, you might well wonder what is happening here, because each carbon atom is surrounded by only 3 groups. And so how does that work? Like, what is actually happening to the carbon atoms in graphite? Well, to answer that question, I think it's actually helpful for us to return to a molecule that we have seen already. In Unit 1, we saw that benzene is kind of a unique molecule because it has delocalized electrons. And I'm returning to our benzene molecule because if we can understand what's happening to the electrons in benzene, we can understand what's happening to the electrons in graphite. So this is a benzene molecule. We saw benzene molecules in our organic chemistry unit. And a benzene molecule has 6 carbon atoms bonded in a ring. We learned that whenever you draw benzene, it's not really correct to draw benzene as having alternating single and double bonds. The correct way to draw benzene instead is to draw single bonds between all of the carbon atoms, and then the electrons that would make up the double bonds are delocalized, meaning that they are shared evenly between all of the carbon atoms. So they're spread out across the molecule. Now that we've learned a bit about hybridization, we're in a better position to understand what's really happening in a benzene molecule. So to determine what the hybridization is for the carbon atoms in benzene, we're going to play the same trick that we did before and just ask how many groups are around the carbon atom. So in this carbon atom, how many groups do we have around it? We have 3. 1, 2, 3. And so if there's 3 groups around an atom, we've learned that the atom is sp2 hybridized. So this is what sp2 hybridization looks like. Here we have an isolated carbon atom that has not hybridized. And then here it's made some sp2 hybrid orbitals. So these sp2 hybrid orbitals are made by hybridizing 1 s orbital and 2 p orbitals. And then one of the p orbitals is left unhybridized. And so the delocalized electrons in benzene reside in these unhybridized p orbitals. And so this image is depicting that idea. The first image is only showing the sigma bonds in the benzene molecule. And so the first image is only showing the sp2 orbitals in the carbon atoms. Okay, so we can see our carbon atom has its sp2 orbitals. And by overlapping its sp2 orbitals with neighboring atoms, it's able to pair up the unpaired electrons in its sp2 orbital. So this image shows all of the sigma bonds in a benzene molecule. Now, each of the carbon atoms has an unhybridized 2p orbital. So that's what's shown in the second image. We're showing all of the unhybridized p orbitals in our carbon atoms. And we learned in this unit that unhybridized p orbitals form pi bonds. And so in a benzene molecule, these unhybridized p orbitals form pi bonds. It's just that the pi bonds are delocalized. So you can see that we've made some pi bonds that are spread throughout the molecule. Okay, so that's what's happening with the orbitals in a benzene molecule. So each carbon atom is sp2 hybridized, and the delocalized electrons reside in the unhybridized p orbitals. Now in graphite, it's basically the exact same situation. Every carbon atom is sp2 hybridized. So you can kind of think of it this way, if we just go back. In our benzene molecule, this carbon atom was bonded to a hydrogen. So let's imagine for a minute that instead of a hydrogen atom here, we had a carbon atom. Well, that's basically what's happening in graphite. In graphite, every carbon atom is sp2 hybridized, and every carbon atom is bonded to neighboring carbon atoms. So all of these carbon atoms are sp2 hybridized. Now, each of these layers has a bunch of carbon atoms that are sp2 hybridized and are all bonded to each other. Each of these layers of carbon atoms are attracted to each other through London dispersion forces, which we've learned are weak intermolecular forces. So that's really not a very strong force holding these layers together. And that is why graphite is such a soft material. And that's actually really what makes it useful as a material to draw with. Whenever you draw with graphite, what's happening is the layers of graphite are actually being peeled off the end of the pencil and deposited onto the page. So the layers get peeled off as you draw with the pencil. Now you can actually have some fun with this. There's actually all sorts of crazy structures that you can make with carbon atoms that are sp2 hybridized. So each of the carbon atoms in this molecule are sp2 hybridized. They all have 3 groups around them. Okay, so there are delocalized electrons all around this structure as well. This structure was discovered a few decades ago, I want to say in like the 80s or 90s. Some scientists discovered that carbon atoms can bond into this crazy shape that actually looks a lot like a soccer ball. And this was very surprising. I mean, scientists had been studying carbon forever. We've known about carbon for thousands of years. And then these scientists just discovered that there was an entirely new form of carbon that had never been known before. People have known about graphite forever, and people have known about diamonds forever. But this was just totally unexpected. It wasn't known that carbon atoms could bond together into these kind of fun shapes. The name that was given to this molecule is Buckminster fullerene. And it's given this name after this architect, whose, I think, first name is Richard. So his full name is Richard Buckminster Fuller. And it's named after this architect because he popularized these dome structures that you can see kind of resemble the shape of the molecule. They're also sometimes called buckyballs. And they really are pretty well shaped exactly like soccer balls as well. So scientists have found that carbon atoms really do bond in this way. And when this was discovered, scientists immediately wondered if you could bond carbon atoms into other molecules with different numbers of carbons. And so these are some examples of other fullerenes. C60, I think, was the original. That's the one pictured here. It's the one that looks a lot like a soccer ball. But these are other fullerenes that have been identified. So C60 has 60 carbon atoms, and then C70 has 70, and so on. Okay, so carbon can definitely surprise us. Carbon atoms can bond into some pretty crazy shapes. There's also an image in this PowerPoint of so-called carbon nanotubes. So carbon nanotubes are also made of sp2 hybridized carbon atoms. And as you can see, they are basically forming a tube-shaped structure. And this is actually quite an exciting development to scientists because these nanotubes, as the name suggests, are very, very small. They also conduct electricity because there are delocalized electrons. So this is an electricity conducting material. And it's also very, very strong because the tube has a bunch of carbon atoms bonded basically into one long molecule. So there's a variety of applications that people are hopeful that carbon nanotubes could be useful in. It could be very useful one day in electronics because you basically have a very strong, very small, and electricity conducting wire. It could also potentially be used in artificial limbs, for example. So it could have some medical applications because it's very strong. It conducts electricity. So if you need electricity being conducted in, some electronic component of your limb, it could perhaps serve that role. Another nice thing about carbon nanotubes is that they are made of carbon, which is an organic substance that our bodies are very used to. So, if you use these carbon nanotubes in your body is not likely going to reject them because they are made of an organic material. So carbon is actually quite an exciting element. A lot of people think that carbon nanotubes and graphene are materials of the future. I'll just make a comment and say that graphene is just one layer of carbon atoms. So graphite is when you have a bunch of layers that are kind of stacked on each other and are weakly held together. If you had just one layer, you would have a sheet of graphene. And so it's basically a very strong sheet that can conduct electricity. So a lot of people think that these are the materials of the future. You might well see graphene and carbon nanotubes being used for different things in the coming decades. Okay, I think this is pretty well the last slide. This slide just introduces the next reading that you'll do as part of today's task. The next reading that you will complete is about glass. And glass is made by heating silicon dioxide. Silicon dioxide, it turns out, is also a covalent network crystal. It is the most common compound in Earth's crust. It will say in the reading that silicon and oxygen are actually the two most common elements in Earth's crust. And silicon dioxide forms these covalent network crystals. And so quartz is actually just pure silicon dioxide. So this sample of quartz is just made up of the covalent network crystal for silicon dioxide. Now, you often don't find crystals of quartz lying around, but you definitely, I'm sure, have played in sand before. And sand contains a lot of quartz. If you actually just look at a sample of sand with your bare eyes, you'll probably notice that some of the grains of sand are kind of clear. Many of those are small pieces of quartz. So there's lots of silicon dioxide around. There's lots of it in sand. And silicon dioxide is the key ingredient in glass. That's actually what glass is made of. Glass is made by heating silicon dioxide and then letting it cool. And the resulting material is kind of interesting. Glass is actually kind of a unique substance. It has some interesting chemistry that you'll have an opportunity to learn about in the reading. Okay, so that is your next task. It is to read about glass. That's the second excerpt that I provided today. There are no textbook questions. I wanted students instead to just read up a bit about some of the stuff that we learned about. Since this was the last lesson in Unit 2, and since we've already done the Unit 2 test, I didn't really think there was much point in giving textbook questions. So your task is just to read about glass now. So I hope you enjoy learning about glass. I think it's kind of an interesting reading. And yes, as I said, our next lesson is going to be starting Unit 3. Unit 3 is on energy changes and rates of reaction. So we're going to get into that material on Monday. And so I hope that you all have a good weekend. And I will see you all on Monday, whether it's through a video or in person.